Thanks very much. Yeah, I think I'm on. So thanks for the invitation to come and talk about Planck and the cosmology that we've been able to learn from it, from its full mission of data, actually. It's a satellite that flew for a few years, isn't it not on? Interesting. It definitely looks like it's supposed to be on. It's on? Super. Okay, let's try that. Better? Good. Okay. So I want to show you some of our results, our main data that we're extracting cosmology from, the main statistics we're using, and what we see is kind of the key cosmological results. So this is drawing on the work of a huge number of people and a huge number of groups. It's a large collaboration of people, and some of their logos are pictured here. This is definitely not single-person work. This is large collaboration work. Okay, so what I want to show you first is what is our main data that we use to talk about things like primordial fluctuations, testing inflation, testing the contents of the universe. And our main data to begin with really are maps of the microwave background sky. And I'm going to show you more or less 3 of them because it's 3 that we're currently using for cosmology. This is a map that you've perhaps seen more frequently than the other ones I'll show you, which is an image of the temperature anisotropy in the microwave background. So the temperature of light at 400,000 years at recombination when the universe transitions to being neutral. We're capturing the fluctuations in that light that more or less trace the density fluctuations in space at that time at 400,000 years. And we've now mapped it out. This is an all-sky map unwrapped onto the screen. And we've now sort of over the last 20 years, we've kind of zoomed in on these features with higher and higher fidelity, now at high resolution and high sensitivity measured from Planck. And these temperature fluctuations, the scale here is tens to hundreds of microkelvin. These are fluctuations about the mean temperature. Small linear fluctuations that allow us to capture the physics of what's happening after 400,000 years and trace it back from inflation, perhaps, or whatever mechanism it was that put in the initial fluctuations through to the time we capture them. So this is the one that you've probably seen more. We're now, to do our cosmology, we've got new images of the sky. And the second one is the polarization anisotropy of the microwave background. So what I'm showing you here, they're not as pretty pictures. There should be prettier pictures coming soonish from Planck. We can measure the temperature of the microwave background. We can also measure the polarization of the light. You can measure, and so the physical thing we measure are Q and U Stokes vectors. So polarization with this orientation in Q and this orientation with U. And we can map that over the sky as well as the temperature. And that's shown here top and bottom for the Q Stokes vector and the U Stokes vector. And we're starting to see, and we're seeing these anisotropies, the gray plot has got lumps and bumps in it, and these anisotropies are tracing the physics of what's going on at recombination as an independent probe to the temperature. But it's the same physics. What we're seeing, the temperature of the CMB traces roughly the density fluctuations in the universe at 400,000 years, and the polarization roughly traces the velocity. So we have this tightly coupled photon baryon fluid that evolves after primordial fluctuations are put in. And we capture what that fluid is doing at 400,000 years, both in density, its density and its motion of overdensities. I'm just showing you a zoom in of a little patch of the sky, about 100 square degrees, a small region, sort of this big, measured from a ground-based telescope called ACPOL, that complements Planck by being able to zoom in a bit more detail on the polarization. And here you can sort of see the fluctuations. These are anisotropies in the polarization of these 2 Q and U Stokes vectors. And it's not coincidence that your eyes will see a pattern like this in the top one and this in the bottom one. That's a signature of an E-mode type pattern of polarization, which is the kind of, if you take a polarization map of the sky and you look at the divergence part of the map and the curl part, The divergence part is the thing that we think traces the motion of the fluid, the photon-barren fluid, and that's what we're seeing in this signal here. The other part that we could see is a B-mode, a curl-type polarization that we haven't yet seen, but I'll come back to that. Okay, so we get to trace we have temperature of the CMB, we have polarization of the CMB, and now we also have this new one, which you'll see increasingly over the next decade, which is the anisotropy in the lensing potential of the CMB. So the microwave background comes to us and gets gravitationally distorted by cosmic structure that lies in between us and when the CMB set off. And typically a photon will get deflected by a couple of arc minutes, very small amount of angle on the sky. And so we can think of it as, you know, the temperature of the CMB we see in some direction of the lensed CMB is the unlensed CMB from some original direction plus the gradient of some deflection field. So a distortion angle that's given by the gradient of some lensing potential. And that lensing potential, the thing that bends the light, is an integral of all the matter lying between us and last scattering. And that's useful because being able to probe the integral of everything that's lying between us and last scattering gives us a handle on things like the geometry of the universe. It tells us more about the dark energy, about what that could be. And also it tells us about the mass of neutrino particles. So this is kind of an exciting new thing to be able to see. And so in the same way as the CMB temperature anisotropy, where you see blue spots, there's slightly less lensing in that direction. And red spots is like a hot spot, it's more lensing. And so you should think of it where you see red, the integral of the matter between here and where the CMB set off is higher than over there. There's more matter in that direction than over there. And this kind of where we are right now with these lensing maps is sort of, you could think of it maybe like how Kobe was for the CMB temperature. As in these fluctuations you're seeing them on large scales. They're still a bit noisy. But this lensing map over the next decade should take the next steps, should really kind of improve in the same way that we've seen the temperature of the CMB improve. But we're already learning things from it. One question I always get asked and then forget to explain, so let me just say this now, is how on earth do you figure out what lensed the CMB when you just get to measure light that's been lensed? A cartoon of what happens to this light is below. This is a little snapshot of part of the CMB sky before and after being distorted by intervening structure that's bending the light around it. And it's a very small effect, but something that you can see slightly. There are coherent shifts in the background features because the light is basically being bent around giant cosmic structures. And what we do, we actually use the fact that different Fourier modes of the background signal are not coupled if there's no lensing, but bending around a large object couples different Fourier modes together. And so we construct an estimator of what did the lensing by looking at pairs of the background temperature at some scale and some different scale, length scale. And we couple those together and estimate the lensing signal from that. I'm not going to say too much more here because it's maybe it's too you don't need that right now. But we appreciate it's not a trivial thing to do, and one of the things that we work on a lot right now within Planck and within other collaborations is to get this better. But this is important because this signal is the signal where we hope, and I'll come back to this in a decade. We hope to say we have detected the mass of neutrinos from this, and it will come from an improved measurement of this map. So I'll come back to that. Okay, so we have these. I would say that's kind of our core data. Are these sort of samples, these maps of the temperature, polarization, and lensing of the CMB. We then look at their statistics, and the statistics we look at are pretty much the two-point function of those maps, because for Gaussian fluctuations, which they do seem to be, that captures all of the information in those maps, although we do look for non-Gaussian features too. And so here is the latest power spectrum, angular power spectrum from Planck from this 2015 data. So up here is the variance in the map, or the power spectrum of the map, as a function of angular scale. And these are tens of degrees or more, degree scale here, and then sub-degree scale running along here to smaller scales. And this is the angular multipole moment of a spherical harmonic decomposition. And so we're in this, Planck is sort of beautifully measured with very small errors, the power spectrum now from large scales through to small scales here, right down to these a few arc-minute scales. And shows incredible consistency with that red theoretical model that is our model that's the lambda CDM cosmology. So we do find a model that fits, and it fits very well. And this is a flat universe with this handful of parameters that I'll discuss in the next slide, where we think we're seeing just simple primordial fluctuations evolved through to recombination in a rather simple universe filled with neutrinos, baryons, photons, cold dark matter, and a cosmological constant. And the fit is really good. I mean, so here, down here shows the residuals of this lambda CDM model, the red one, compared to the data. And the error bars are so small that you kind of have to see it on this residual plot. And so anything that isn't this kind of simple lambda CDM model would show up as deviations of these data points around that red line. Now, one thing that your eye, goes to straight away is here. This sort of dip, this lack of power at the larger scales has been seen for a while, is still there, is a curiosity. It's kind of deviant at like 2 to 3 sigma, but not at higher significance. It's interesting. At smaller scales, there are some points that deviate from the line, but not significantly. And actually, something that's happened in the last couple of years with improved Planck analysis is that the residuals of this data with respect to the model have just really squeezed in. So there's incredibly little wiggle room of anything that's not this model compared to the data. And let me just say a bit more specifics about what this model is. Because what we do is we throw in 6 numbers, 6 variables, and a handful of assumptions about the universe when we're predicting the theories that match the data. We assume a flat universe. I'll come back to that. So we assume a flat universe, and we can constrain 3 numbers that describe its contents and the expansion rate of space. And we quantify them by a baryon density, a cold dark matter density, and a peak angle at which we see the C and B acoustic peaks. And that maps onto what the contents of the universe are. So, for example, if I tweak around the amount of dark energy, the dark matter, the cold dark matter, the baryons, that would change the peak angle I see the C and B at. We have 3 numbers that describe those. And we have 2 numbers that describe the primordial fluctuations. We think they're just Gaussian, they're adiabatic, so all the different fluids in the universe trace each other at early times. They follow the same overdensities. And they are described by a power law with an amplitude and a spectral index. And that spectral index differs from 1. It's not, that's one of the big results that's consistent, that's held up with the sort of improved analysis of Planck. It's still there, right? The spectral index is significantly different from 1 that describes the fluctuations. And those are probably the 5 parameters of main interest to this audience. We also have the CMB gets scattered. When the stars light up the universe, the CMB light gets scattered and damps the signal. And so the epoch when reionization occurred affects our signal and is of great interest to many astrophysicists, but perhaps of less interest to this audience. So that's one of our numbers. And we have a bunch of assumptions. We assume the universe is flat. We assume that the dark energy is just a cosmological constant. We assume there are 3 species of neutrinos. We assume the primordial helium fraction is set by Big Bang nucleosynthesis, that it's 25% of the universe. We assume that the total mass of the neutrinos in the universe is 0.06 eV, which is the minimum mass scale that we'd get from neutrino oscillation experiments. We assume there are no tensor fluctuations, no cosmic strings, no magnetic fields, nothing, right? All those things are not in this model. And this is the model that really fits. And you know, we looked for a lot of things that differ from it, and they're just not there. And that's really held up even more by looking at these extra maps of the sky, the polarization and the lensing. So here, what I'm showing you is this is now the power spectrum of the E-mode pattern that sits in the polarization maps. If I take my maps of the C and B polarization, and I look for the pure divergence pattern in them, and then I compute the two-point function of that, then that's shown here, the power spectrum of that E-mode signal as a function of multipole, again, angular scale, large to small scales. Here in blue are the data points from Planck. And in red, this red curve is not fit to these data points. That red curve is just lambda CDM, the lambda CDM model that fits the temperature data plotted on the polarization data. So the fact that this wasn't even fit to the data, you know, says that this model is doing something right. It provides a pretty good fit. One of the residual worries within Planck that's being worked on right now is that if you zoom in and you look at sort of the difference of the data with respect to the red lambda CDM model, there are some more deviating points than you see in the temperature. And we do think there are some residual systematic uncertainties left in the polarization data, at kind of the 1 sigma or so level, probably from some of the temperature signal leaking into the polarization. And that's why the main cosmology results don't use this polarization yet. We sort of looked at it, but really the main results still come from temperature. And that's something that you should see change in the next year. But it's not, you know, we're talking about small shifts. We're not talking about something significant. And we also see the correlation between the temperature and the polarization down here. Again, red curve not fit to the data. It's just the prediction of lambda CDM of the cross-correlation between the fluctuations at the temperature and the polarization of the signal. The third piece of the data is then the two-point function, the angular correlation, the angular power spectrum of that lensing signal, the lensing potential. This then again shows the power spectrum, the two-point function of the lensing signal as a function of multipole. Again, these are degree scales in the sky. Here are the data from Planck. And again, the black curve is just lambda CDM fit from the temperature data. It's not fit to this data. And it provides, and it fits very well. You know, there's kind of this dip here, but it's not really significant. And this is useful because what this allows us to do, so what this measurement allows us to do is do things like, as coming back to neutrino mass, but also at a more simple level, measure the geometry of the universe. That the lensing essentially probes the amount of clustering of cosmic structure at later times in the universe. It typically picks up the size of cosmic structures kind of halfway through the universe's history, dominantly. It's an integral, but that integral peaks kind of halfway through the universe's history. So we're picking up most of the signal kind of at kind of 7 or 8 billion years, but it's a broad kernel. It picks up signal from earlier and from later. And if we had a universe that kind of fit the background CMB data, but was more geometrically, was closed and had less dark energy than lambda CDM, it would actually produce more lensing because you'd have more clustering in the universe. So if you have more clustering happening, you boost the lensing signal and you would push that whole curve up. And that's given us these strong constraints on the curvature of the universe. So here. I'm showing you here the fraction of the universe energy density in dark energy, or cosmological constant here, versus matter density here, where the dashed curve is a flat universe. And anything off that flat curve is in this direction is a closed universe. And it used to be with the CMB, you could go all the way down that geometric degeneracy down to 0 dark energy. And now you can't, because the lensing gives us a lot of new information. The lensing prohibits, you know, a vastly closed universe. And so let's just concentrate on that blue contour. These are the 95% confidence limits for those two contents of the universe. And you see it's tightly closed in around the flat line. And if I then express it in omega k, the curvature of the universe, then just with the CMB, I get a 2%, these are 95% limits, that the maximum deviation from flatness is 2%, just from the CMB. Now, if I then add in the positions, if I look at then galaxies at later times, and I look at where the galaxies are, this is from the Sloan Digital Sky Survey, galaxies are typically preferentially separated by a particular distance. And that's seen here from the Sloan data. They're typically separated at this kind of 120 megaparsecs, where a megaparsec is a typical separation of of pairs of galaxies. There's this peak separation, and that peak separation gives us a handle on the expansion rate of the universe at later times. And if we throw in that as well, then you get down to a 0.5% constraint on the curvature of the universe. That's that red curve here. So really, there's any wiggle room from flatness is vanishing. If I look at now at the primordial fluctuations, this shows our current constraints from both Planck and data including new data from the South Pole telescopes, the BICEP 2 and Keck array. Down here is this spectral index of fluctuations that I mentioned before, where a value of 1 is scale invariant fluctuations, and n less than 1 has less power at smaller scales and is what we would naturally expect from many simple models of inflation. And this is, as I said, this is one of the main results from Planck, is that if I just look at that red 95% contour, I'll come back to this number in a minute, it excludes 1 at high significance. And it zooms in on kind of 0.96, 0.97, that range. But now, obviously, the thing that's certainly of interest is, do we see any gravitational waves? So if inflation happened, we would expect to see a background of tensor fluctuations. We expect tensor fluctuations that would source a background of gravitational waves. And the strength of those, the size of that signal will depend on the energy scale of inflation, and it's something that obviously we all would like to know if we can see it and what it is, because that would tell us a huge amount about both whether inflation happened and its characteristics. And so here is this, we characterize it by a tensor to scalar ratio, how big the tensor fluctuations are compared to the scalars. In a given slow roll inflationary model, every model will have a predicted space point on this NSR plane. So here, for example, would be a slow roll inflaton potential with a phi squared shape. Here would be a phi shape. And so here, so with the Planck data, we limit this space in the NSR plane to here, where you can just about get this phi squared potential, but a phi to the 4 term is gone off that space. It's no longer works. And those just come from looking at the temperature anisotropy. But what we're really all looking for is this specific prediction that gravitational waves will put in a polarization signal that has a curl part that has this kind of pattern in the polarization. And we have not seen that yet, a primordial B-mode signal. And that's, we all heard last year that we thought we might have seen this from the BICEP 2 experiment at the South Pole, who did see a B-mode signal, and would have put, if the signal was just pure gravitational waves, would have put us up there somewhere, a point that's actually inconsistent with Planck. But there's actually no evidence that it's gravitational waves, and everything's pointing to the signal that was seen just being emission from our own Milky Way galaxy. So that right now, by including information from the Planck satellite that tells us more about the signal from the galaxy, we've managed to sort of clean up the data from BICEP 2, clean it up, and put actually a new limit on the tensor to scalar ratio. And that's what's shown here in green, down here. And that's kind of interesting. And then the blue contour is if you add in the lensing data and external data. But they're rather similar, but a bit squeezed in this direction. But either of these two curves, so bring this phi squared potential into kind of then disfavored at more than the 95% level. I mean, it's not 5 sigma, but it's certainly not preferred by the data. And what many of us are doing to move beyond Planck are to try and make a detection kind of in this kind of level if the signal is there to be seen, or at least push down the limits, down to here or below, because many, that's obviously of great interest for constraining inflationary models. But the current limit is R of less than 0.09 right now. There's no evidence that anything that we have any fluctuations that don't just obey this power law Gaussian adiabatic description, okay? And that those constraints have really tightened with all the Planck data. We can look at the fraction of primordial fluctuations that could be non-adiabatic, so where the fluids at early times don't follow each other at early times, as you might expect if they were imprinted by inflaton fluctuations decaying to form all the fluids in the universe. We can characterize that by some parameter alpha that shows the deviation away from adiabaticity, and that is restricted to be less than a percent or so, and even less so with temperature, and even less if we include the polarization data, which is it's still early days for that. And there's no evidence for non-Gaussianity. The constraints on this FNL parameter that describe the deviation, or a particular kind of deviation from non-Gaussianity, where 0 says they're Gaussian, is now tightly constrained to be 2.5. There are different types of it for different shapes of non-Gaussianity, 2.5 plus or minus 6. And all these other two numbers here that show also are consistent with 0. So no evidence of that from the CMB. And no evidence that the primordial fluctuations deviate from a power law. So any kind of scale dependence of the spectral index is constrained at the kind of 1% level. It can't vary more than that. And there's no significant kind of features in the spectrum that could say you have some significant oscillation or some significant boost at some scale that could be indicative of some more unusual model. We're just not seeing it. We've learned a lot about neutrinos with Planck and with ground-based experiments. We're able to measure the effective number of species, which for us in cosmology could mean neutrinos, the effective number of relativistic species. That could mean neutrinos. It could mean other things. It could be axions. It could be anything that produces a relativistic background. We would count as being these relativistic species. And so what we do is we assume it's all neutrinos, and we constrain the number of them. Okay, so and we allow that to be a continuously variable number. We don't just assume it to be integer values. And so I'm showing you here the constraints. Well, let me just give you the numbers that we have, which is the number of neutrino species, or the effective number of species, is now pretty tightly constrained at 3.1 plus or minus 0.3 or 0.2 at a 1 sigma level, depending on whether or not we include, this is Planck data, and this includes galaxy position data. And this has really taken a big, and this comes from the fact that if you increase neutrinos, you basically sort of, imagine you're switching radiation from photons that are coupled to baryons to neutrinos that are not coupled to baryons. The sound waves at the early times propagate differently in those two fluids. And so neutrinos additionally damp the power spectrum and slightly shift the peak positions. So getting a measure of the damping tail from Planck, and then increasingly with polarization, you can really limit how much non-photon radiation you have in the universe. And this number, you used to be able to have like 10 in the CMB, just like 5 years ago. 10 was fine, right? So the fact that it's, even 4 now looks pretty disfavored. So this shows that number as a function of baryon density. And this if I look at any of these combinations of data, 4 is really on the edge. Now again, you could have some different relativistic species that could contribute a fraction of an n. It could be 0.2, 0.1, 10 to the minus 5. And that's still in there, but we are squeezing down on the possibilities there. And in the next few years, that should be halved or better, that uncertainty, from measuring the CMB even better. And we can also look at the primordial helium fraction, and that's also now much better constrained with Planck. If I look at neutrino mass, there are many effects of neutrinos, but just the one I want you to sort of have carry dominantly at the moment, because it's the one where I hope to make best progress, is if you switch cold dark matter, if you take some of it and turn it into neutrinos instead, then the universe that has more massive neutrinos has more suppression of clustering of cosmic structure. Because those neutrinos, even if they're massive, they started off relativistic in the early universe. They basically behaved like radiation because the universe was so hot. So a massive neutrino behaved like radiation and then like cold dark matter later. And the fact that it had this epoch of behaving like radiation, it free streamed out and it doesn't cluster like cold dark matter. And so you get less clumping of stuff in the universe and less lensing. So you tune up the neutrino mass and you push down the lensing power spectrum. And there are other effects too, but this is the main one to think about. And that's given us this measurement of this constraint on the neutrino mass, the sum of the neutrino masses that's less than, this is too many decimal places. I'm sorry, I did not choose these number of decimal places. 0.68, right, or 0.7, I'd say carry 0.7, right? That it should be less than 0.7 EV at 95% confidence. And if you add in the galaxy information, then it's less than 0.23 or 0.2 EV. And this is kind of interesting because this is getting into the regime of, we think that there should be a signal at 0.06 EV or greater. We have to be careful because we're doing cosmology and this is all indirect measurements. We're not seeing neutrinos, we're just measuring their effects cosmologically, so we have to be really careful about whether it could be mimicked by other things that we don't understand yet, like dark energy. And there are some degeneracies with those, but they're not really strong. And so this is where in the next 10 years we're hoping cosmologically to actually detect neutrino mass. Again, with these caveats of it being an indirect detection. But I think we're in an exciting regime. Let me just raise a couple of problems or clues, and then I'll stop. I'm saying, giving maybe a slightly. We see nothing in the Planck data and in other CMB data that says that we need anything that's not just this simple lambda CDM model. It's kind of a bit freakishly good fit. That if I were to raise any problems or clues of where we might see something new, some new physics, right now, if we look at how galaxies are lensed around large-scale structure, we call cosmic shear, the current measurements of the size of clustering, when this number kind of quantifies size of clustering, okay, this green contour doesn't quite overlap with this black one, and this black one is the Planck one, and this green one is kind of the one from lensing of galaxies. They don't quite overlap. I think it's more likely that the measurements of the lensing of galaxies is still in early days and might have systematic uncertainties. So I don't think that this is a huge problem, but it's potentially interesting. The peaks of the CMB are a little bit too smeared out. If we introduce this strange parameter that I call A lensing, A lensing should be 1 if the peaks are all completely as I expect. And actually, this is a bit too busy a plot, but this blue curve here is the preference from the Planck temperature data, and it prefers a slightly higher value. And so it's that the peaks are slightly more smeared out than I'd expect in just lambda CDM. But it's not a physical parameter. This is not a physical model. But if one has a physical model that actually does predict a bit more peak smearing, then there's some room in the data for that. And these large scales, the fact that this is dip in power at the largest scales is very interesting. And I think we have to look in the polarization data and just keep it in mind that it's there, even though maybe it's not hugely significant. Okay, so right now, the data from Planck, the CMB data, they demand lambda CDM kind of more and more confidence. And so it's got to look like lambda CDM, even if it's not. And in particular, if it's non-inflation, it's got to look a lot like inflation, if that was the thing that put in the primordial fluctuations. And we're busy searching for gravitational waves. And I think the neutrino sector is an area that holds a lot of promise for the next decade in cosmology, and I hope we have a lot of interesting further things to say with the next generation of experiments.
Thank you for the great overview. A couple of quick questions. We have time. Yeah.
Would you like to comment something about neutrino mass hierarchy? What are the prospects?
Yeah, I would. Yeah. So really, realistically, for a long time now to come, we can only measure the total mass. So we're slightly sensitive to the hierarchy, but mainly we're sensitive to total mass. And so if it's inverted, then it will be at least 0.12 eV will be the total mass sum, and we'll get there sooner. Yeah, so we could detect an inverted hierarchy, I think in 5 years, cosmologically, with the caveats, right? So that will be interesting.
And you also mentioned degeneracies with other.
Yeah.
What is the most dominant source?
It's a great question. Actually, so right now, me and my PhD student is actually working on a paper to really push, explore kind of as many as possible. If you just want to use the cleanest probe, so CMB lensing and the galaxy positions, then they're most degenerate with curvature and with the dark energy equation of state. So if you allow the dark energy equation of state to vary with kind of a 2-parameter model, W0, WA, then it could as much as double the error on the neutrino mass. And those are the main ones. But there we're kind of then other data should help break these degeneracies again. But those are the two main ones, because it's basically neutrinos suppress clustering, but you can change the expansion rate to look a bit like that. That's why those are degenerates. But they're not completely the same.
The last one.
When you say that the quadratic model is disfavored, that refers only to single-term potentials. Right?
That's right. Yeah. Sure. Definitely. Yeah.
Oh, yeah. Okay. One more. Just take that.
You were talking about the time frame. You said that in the next decade we will know the mass of the neutrino to an order of magnitude. Using which experiment?
Oh, yeah, it's a good question. There's two prongs. One is improving the CMB lensing. And so for CMB lensing, we've got what we call, or in DOE speak, stage 3 CMB experiments. These are experiments from the ground that will map half the sky from the ground. And that's the Advanced ACT telescope in Chile and the South Pole Telescope, third generation experiment. So both of the ones that have already been doing small-scale CMB, they're putting on more detectors and covering more sky. And that will get us kind of part the way. Then there's CMB stage 4 that is planned but not fully funded yet, which is the natural extension of all these ground-based experiments, which we're saying we're not going to get a new satellite anytime soon. What we can do is use, or I say that, there are strong proposals for smaller satellites to measure the larger scales. But to map out the whole sky to get neutrino mass, you want to get as much of the sky as possible at higher sensitivity. And so from a mixture of these ground-based telescopes in Chile, the South Pole, potentially even Greenland, will do that. At the same time, the measurements of galaxy positions will improve with the DAISY galaxy clustering survey that's starting in a couple of years, that moves on from the Sloan Digital Sky survey. So it will be the combination of, I think the thing that we can actually make a detection from will be what we call CMB stage 4 plus the DAISY galaxy clustering survey. So, yeah.
Okay, I'm afraid we have to move on, and we can talk to the speaker later. Yeah.